Good afternoon and welcome to the Computer Security Seminar from Purdue University. Our speaker today is Rafae Bhatti. He's a PhD student from the School of Electrical and Computer Engineering. His faculty advisors are Arifka Four and Elisa Bertino. He'll be graduating with his PhD this spring, and his topic is what he'll be covering today with us, X-Federate, a policy engineering framework for federated access management. Rafae?
Thank you, Randy. Well, good afternoon, everyone. I'm pleased and honored to present the CERIAS Security Seminar today. The topic, X-Federate, a policy engineering framework for federated access management. So, let's get started. Here's an outline. I'm briefly going to introduce the problem. What is the federated access management challenge? Why is policy-based system an appropriate mechanism to address that challenge, and what are the shortcomings of existing policy-based approaches? This will lead us to policy engineering framework, which is my primary research contribution for my PhD dissertation. It comprises of a language specification and a UML-based meta-model. I will then discuss a federation architecture that realizes this framework. Toward the end of the talk, we will have an application that discusses an example of a healthcare federation. So we have used our policy engineering framework and applied the methodology toward a healthcare federation example. And if I can connect to the internet, I'll probably have time for a prototype demo. And we will then conclude and take any questions you may have. Okay, so what is the information integration challenge? This picture here gives the high-level overview of the problem. This could represent, among other things, your national cybersecurity infrastructure. And these domains are a series of interconnected domains which are, this interconnection is enabled using collaborative architecture such as grid or peer-to-peer systems. And at the heart of this infrastructure is the federated databases. Federated databases are heterogeneous information sources, and they are characterized by distributed, potentially mutually untrusted domains. And the problem that I'm going to address here is security in federated systems. So at this point, you might ask that, isn't it just a network of databases? And if so, isn't network security enough? Or for that matter, isn't database security enough? And if the answer to that question was yes, then I wouldn't have worked on the problem at all, right? So I'll take some advice from history to answer that problem. SQL Slammer and Code Red were the two of most deadliest worms in computer history. And those worms brought home a message. They attacked a weak point in many companies' systems, the database, and showed how interconnected databases can provide security vulnerabilities. Most of you would be aware of security vulnerabilities that are exploited through malicious code. Intrusion attacks are used to inject malicious code. However, these vulnerabilities are not only exploited through malicious code, but also through legitimate but unacceptable accesses. The link right here on the slide gives a very good idea about such legitimate unacceptable accesses that occur to the personal information of every one of us, stored in interconnected databases of online retailers, mortgagers, insurance providers, etc. Why? Because of inadequate access control policies. I was going through this recent March issue of Communication of ACM magazine, and it always has a security watch or an inside risks column on the last page. And this month, the title is Real ID, Real Trouble. And I thought it would be interesting to discuss that because it talks about setting up a real ID based on the Real ID Act of 2005, a federated information system which would involve the use of a federally approved ID card to travel on an airplane, open a bank account, collect Social Security payments, and take advantage of nearly any government service. And some noted security experts have pointed out some security risks, including, quote, the biggest risk of a national ID system is the database. Any national ID card assumes the existence of a national database, and large databases always have errors and outdated information. So imagine, as shown on the slide, 500,000 interconnected databases. So we don't really have to wait for intrusion attacks or malicious code for a security breach to occur. It's potentially occurring every day. We need access control management. All right. So I've talked about the motivation behind access control management and why it would be needed in federated systems, highly interconnected database systems. Let's talk about some of the key access control policy challenges. And why are these systems much more difficult to manage than traditional systems? So the key principle in federated systems is autonomy. Each domain maintains autonomy to its information sources. And by that I mean that each domain has the right to exercise its own access control policy. For example, domain B might say that a user John has access to a level 2 resource, whereas domain A might say that the same user has access to a level 1 resource. How do you match the two? This leads us to the problem of decentralized administration. Each domain enforces its own access control policy, and so the problem is that who is going to control the policy in the federated system? Attribute-based access control. Suppose domain D has a policy for user John and also domain E has a policy for user John. But the question now is, should that policy be based on the ID of the user or some attributes that the user has? If the policy is based on the ID, then domain D does not necessarily know about the ID of every single John in domain E. Remember, they are distributed and untrusted domains. So they wouldn't know in advance about the IDs of every single user in other domains. On the other hand, if the policy is based on attributes, then they can potentially serve all the users who satisfy that attribute. Leading from the previous argument, we have another problem. Even if you assume that domain D knows the ID of every other John in every other domain, this leads to a rule explosion problem, because you would have to replicate the identity databases of one domain across all the other domains. Federation. Domain E might have a policy for user John to access a level 1 resource in domain D. However, the challenge here is that for John to be able to access that resource in domain D, you need interoperable protocols to be able to federate those credentials to the other domain. If you write your policy in a totally different format, then it wouldn't be understandable to the other domain. And last but not the least, constraints. Federated systems have a pronounced requirement for constraint specification because in an interconnected system, it is very important to give the access privileges only when absolutely necessary so that the exposure to the information is minimized. For example, many of us use online banking and other online systems, and most of these systems have all or nothing authorizations for your customers. You enter your username and password and you get access to everything that every other person in that every other customer gets. However, it's much more important in federated systems that the access is granted only when it is absolutely needed. For example, if a billing clerk in your financial institution has to issue you a monthly bill, they only get to work when your billing cycle completes. And a billing cycle typically ends at the end of the month or the beginning of the month. So it's only intuitive that the billing clerk should get access to your information only within the certain time frame that they have to work in. And so this leads us to the idea of constraints. So constraints can be of multiple types. You can have semantic constraints. What that means is that John may have access to level 1 and level 2 resources in domain A, but not at the same time. This is called separation of duty. Other kinds of constraints are temporal and non-temporal contextual constraints. For example, John may access level 1 resource in domain D, but only on Wednesdays and only from emergency ward. Okay. So these are 6 challenges that we have identified for access control policy design in federated systems. Let's see. You may be thinking that haven't other people already worked on policy-based systems, or haven't access control challenges been addressed in distributed systems before? So the idea is that these requirements, like I said, have emerged because of the recent emergence of modern collaborative architecture such as GRID and peer-to-peer, which have helped realize the vision of federated information sharing. So we will compare the existing approaches based on the 2 key aspects: the goal of the policy system And in our case, we have to see if it meets the needs of the federated information sharing and the design of the language used to construct the policy. Is the policy flexible and maintainable enough? All right. So in terms of policy goal, there have been policies designed for network security, database security, and even code security. But because of the fact that the collaboration architectures have only recently emerged, so these systems do not address the federated information sharing requirements that we have addressed before. On the other hand, the systems have policy languages which are feature-rich, and they are based on formal model, formal grammar specification, and XML DDDs. But such languages offer limited flexibility and maintainability. They are not based on any modular language components. They don't have any construction or maintenance methodology, and there's little support for deployment and integration. As you might imagine, in federated systems, it's much more important that the policy you should be able to deploy and integrate the policy because there are multiple systems that are interoperating. And so deployment and integration becomes a very important concern. Okay, so what needs to be done? We view that policy should be considered as a program. You need to design modular language components, and your policy should be configurable and maintainable using same methodologies as other software. And you should be able to deploy your policies in a uniform manner. The idea there is that just like you take a programming language like Java and C and develop a program to satisfy the requirements of your application, similarly, we need to develop a policy language to construct policies for the security requirements of the end system. So we propose a development methodology based on the principles of software engineering, and we apply that to construction of policies. And keeping in mind the requirement for component-based, language being based on modular components, we use a component-based development approach. So our approach is called policy engineering. The motivation is a standardized methodology for design of policies using principles from security management and software engineering. And the benefit is that it provides uniform development and deployment of interoperable policies for access control in federated systems. Another benefit of our approach is that there are complementary efforts such as the Common Information Model by the Distributed Management Task Force. That model is designed for the network management policies. And our vision is that if policies are constructed using well-known methodologies, then policies for network management and this database access management can interoperate in a federated environment. And the work on my PhD thesis recently got accepted for Transactional Software Engineering, which is a flagship journal of this community. And so this gives us some recognition for our work. Which is good in a sense because we proposed a novel concept of interleaving software engineering principles for the design of security management policies. And we believe that there's a lot of motivation for this idea, and we see a lot of potential for this work in future. So, to summarize our contributions, we have identified and developed key language components that address the requirements that we have just discussed. To satisfy the requirements for attribute-based access control, scalability, and federation, we have developed attribute-based credentials. For autonomy and decentralized administration, we have developed declarative rules. And to satisfy the constraint requirement, we have developed constraint definitions. And our policy engineering methodology brings these components together in the design of our policy language and a UML-based meta-model. So this was the introduction. And the motivation behind the work. Are there any questions so far before we go into the detail of the framework itself? All right. Let's keep going. So the policy framework consists of a policy specification language. Our policy specification language is based on an extension of the role-based access control model, which is recognized for simplified administration. Our language is called XML-based Generalized Temporal Role-Based Access Control, and it extends RBAC for the extension necessary for access management in federated systems. So let me give you a very brief overview of RBAC. RBAC comprises of 5 main components: users, roles, permissions, and a user-to-role assignment relation and a permission-to-role assignment relation. The key idea being that permissions are assigned, instead of assigning permissions directly to users, permissions are assigned to roles. And the users obtain those permissions by acquiring the roles. Okay. So how do we represent the requirements in terms of the role-based access control model? We have designed a formal grammar called X-Grammar, which follows the BNF syntax, but the key distinction is that the grammar is designed to allow translation into XML schemas. So one of our contributions is that we extend BNF syntax to allow compatibility with XML schema specification. What this means is that the terminal symbols in our grammar can have attributes, and the attributes have data types. So this is at the top level syntax of our grammar. As you can see, the start symbol is the policy definition, which reduces to a policy terminal symbol. The terminal symbol has an ID and a name attribute, and the type of which belongs to the XML schema specification, and therefore the XML schema serves as the type system of our language. There are 5 non-terminals in this policy terminal symbol, and they represent the 5 components of the role-based access control model, namely the user, role, permission, user-to-role assignment, and permission-to-role assignment. And we have a non-terminal for constraint definitions, which represents the extensions to the basic RBAC model that we have proposed. So we will go into the details of all these non-terminals because they represent the language components in our framework. To summarize the language, we have 3 language components: credentials for user, role, permission, assignment rules for user-to-role and permission-to-role assignments, and constraints, which include temporal and non-temporal constraints. All right, so before we go into the detail of the language components, I would like to give you a high-level overview of the framework. The user, role, and permission credentials are used to construct assignment rules, and the constraint components are then applied on those assignment rules. And therefore, using our methodology, the 3 different types of components come together to compose the overall policy specification. And this picture gives you the idea of how we emphasize modularity and flexibility in policy design. So we will now go into the detail of each of these components and take a look at the policy and the X-Grammar. So this is the user credential. The convention that I've used here is that all non-terminals are represented in bold. And so a user credential includes the credential type. A credential type is used to associate a user with a particular category. To give you further motivation, consider a federated digital library example where multiple academic institutions come together to allow their users to share library resources across their online libraries. So consider that Purdue has a database of users, John 1, John 2, and its library has a resource called libresource level 2. And imagine other users from other institutions trying to access the level 2 resource from Purdue library. At this point, you have 2 concerns. Number 1, how is Purdue going to recognize the students from other universities if it does not know their identities? And as we said, if you replicate the identity database, if every school replicates the identity database from every other school, you will lead to the problem of rule explosion, where you will need to maintain one set of rules for every single student across the entire federation. So to minimize these problems, we propose the following strategy. Suppose it is known that Purdue allows students to borrow books who are over 18 years of age and have a valid state ID. This gives us a set of attributes that can be used for access control. So in this case, the date of birth and a state ID or a driver license number can be used as an attribute for a group of students who can access a level 2 library resource without having to require their identities to be known in advance. So here's an example of such a policy. Note that the policy is not based on a given username. So an anonymous user can request a resource, and the ID of the user is an any keyword in the system. The user provides a credential for accessing resource level 2, and the attributes used in the credential are date of birth and DLN. So any user, as long as they are able to provide a credential issued by their original university or a trusted third party, indicating a date of birth attribute and a DLN attribute, will be able to access services at Purdue library or any other library who accepts those attributes. So we removed the problem of having to know the identity of the users in advance. And we also removed the problem of rule explosion in the policy, because this rule works for a category of users who satisfy these attributes. Similarly, we have a role credential, and a role may also have a credential type. The motivation for having a role credential type can be seen in this example. We take the example of a federated digital library once again and consider two roles in Purdue database. There's a borrower level 1 role and a borrower level 2, who can borrow resources belonging to level 1 or level 2 respectively. So consider a borrower level 2 role, and suppose Purdue wishes to exercise different policies for a grad student in that borrower role and an undergrad student. They might say that a grad student can access books from anywhere on campus, whereas an undergrad student can access books only from inside the library. And you may have noticed that this constraint is actually enforced in our libraries when some books are actually on the reserved desk, and you can only borrow them while you're inside the library. So what is the solution to this problem? One solution is that you can obviously create 2 additional roles. You can say level 2 grad and level 2 undergrad and enforce a separate access control policy. But this will clearly lead to the problem of rule proliferation. So the solution that we use again is the use of attributes. A level 2 role will have a credential for borrower level 2, and the credential will have attributes, class, and location. Based on the value of the attributes of the user who is in that borrower role, you can design the access control policy rule. And we will see an example of that shortly. Before going there, we'll discuss the third credential component in our language, which is permission credential. As you might expect, a permission credential has an object and an associated operation. But what's of interest here is the propagation option on the permission. The propagation option becomes interesting in the case of XML documents, because XML documents are hierarchical in nature. So if you give the permission to the top level element, it may or may not propagate to all the child elements. And so we have 3 different options. Either the permission propagates, does not propagate, or it propagates only to the first level element or all the elements. An example of a permission that we discussed before is a get permission on a level 2 resource. And we use the HTTP get operation in this permission. So coming back to the assignment rule, assignment rules are the second kind of components in our policy language. The key in the assignment rule is the use of the assigned constraint element. And this is what differentiates an assignment rule from an all or nothing kind of an authorization, because in an assignment constraint you can specify assignment conditions based on the credential type that the user or the role is associated with. So here's an example. The role libborrower level 2 can be assigned to any user if the user supplies the resource level 2 credential having a DLN and a DOB attribute. And the condition there is that the credential should have non-null values of both of these attributes. And the logical expression tells us that both of these predicates must be true for this role assignment to occur. Similarly, a permission to role assignment rule. A level 2 resource get permission can be assigned to a libborrower level 2 role if the role has a libborrower L2 credential. And you notice here that the logical expression has an OR operand, which means that either the class is graduate, which means the student is a graduate student, or the location is inside the library. This solves the problem that we discussed earlier, that for instance, if Purdue wants to enforce an online access to its library resources, we can use this policy to allow a role to access the service provided that either the user who is in that role has a class attribute equal to graduate, which means it's a graduate student, or the location from where you are accessing is inside the library. So if you note here, the location is a dynamic attribute, and we need runtime evaluation of a dynamic attribute. So this is something that we have recently extended. We have recently extended our architecture to provide support for location-based constraint evaluation, where we use a geospatial profile of role-based access control model, and we evaluate that at runtime to determine the actual location of the user, and the decision of that access request evaluation is fed back to our access control processor, and we accordingly assign the permission to the role if the user belonging to that role is within the authorized location. So that's a pretty cool concept because it has a lot of application in pervasive computing and mobile computing area. So moving on, the next component is the constraint definitions. Constraint definitions allows us to enforce interval, periodicity, or duration constraints on any kind of event. And the event that we are concerned with is the user to role assignment and permission to role assignment. So to give you an example, this constraint definition defines an interval starting from 1st of January 2005 to 31st of December 2005 with a duration of 1 week and a periodicity of first week in either the 1st, 4th, 7th, or 10th month of any year. If you notice carefully, this periodicity represents the first week of every quarter of a year. And this goes back to the requirement I discussed earlier, such as in financial systems, where your billing cycle might be every quarter, first week of every quarter of every year. And if you want to constrain the authorization of someone based on a billing cycle or based on any quarterly cycle, you can enforce this constraint in your access control policy to minimize the exposure of information for potential unauthorized or unacceptable use. And no other policy language has such sophisticated temporal constraint capabilities. So here's an example of an assignment rule previously discussed, but this time with constraint. So we use the same example as a lib-borrower level 2 role being assigned to a user, but this time we include a periodic time expression ID. And note that this ID refers to the constraint that we have defined earlier. So what this means is that in addition to satisfying the credential attributes that the user has provided, the temporal constraint must also be satisfied for the assignment to occur. And you might notice the flexibility requirement is met because you can include or exclude the temporal constraint according to your own requirements. All right, so we have discussed the policy grammar and the policy components. Let's go to the UML Meta-model. UML Meta-model involves mapping the X-grammar into UML and translating the UML into UML schema. The motivation for the former is that it allows application of existing software engineering methodologies toward policy development, which facilitates our goal for policy engineering. And the second part allows rapid translation from XML schema definitions to program code, which is once again a key requirement in federated systems, going back to our initial development methodology concerning deployment and integration of policies in federated systems. For translation of UML into XML schema, we use UML profile for XML schema. And here's the mapping criteria for that we use to go from X-grammar to UML profile for XML schema. I wouldn't go into the detail of this, but the analysis goes like this. Roughly speaking, a non-terminal in the grammar maps to a class in the UML. A terminal maps to an attribute, and so on. But there are some complexities for which you will have to read my thesis, unfortunately. But I'll just leave that here right now, and I'll give you a more visual view of the UML meta-model on the next slide, which is right here. So this gives you an idea of the depth and the breadth of the UML meta-model, and this also gives a very nice visual representation of the policy grammar that we have developed. It is obviously unreadable at this macro scale. So let's go a little deeper into some of the classes and see the components in a little bit more detail. This is an example of a user credential. As you can see, a user can have a credential type. You also have a permission, which contains an object and an operation. A role definition, which includes a credential type for a role. A credential type can have a credential expression. And there are several other associations of roles, such as constraints and linked roles, which I do not have the time to go into in this talk. Assignment classes include a user assignment object, which can have an optional assignment constraint. And also the permission to role assignment also has permission assignment classes, which can have an assignment constraint. The temporal constraint definition comprises of an interval expression object, a duration expression object, and a periodic time expression object, which can have a start time expression, which defines the periodicity of the event. You can also have separation of duty amongst roles. So this completes the discussion on the policy engineering framework. I will now present a federation architecture that realizes this framework and helps us develop applications using our framework to address requirements of practical systems. So the application that we have used for our framework for the case of my thesis is Federated database schema architecture. And the idea there is that the X-GTRBAC policy schema serves as the common data model for the federated system. The multi-level federated database schema architecture is a well-known architecture and comprises of local schema, component schema, export schema, and federation schema. And the idea here is that the common data model for a federated database schema architecture can be utilized for information sharing and exchange in a federated system. And we provide X-GTRBAC policy schema as a means to act as a common data model for secure information sharing in federated systems. And since our policy schema aligns with the multi-level federated database schema architecture, therefore it can work with all systems that implement that architecture. Examples of such systems are given on the slide. We have talked about most of the requirements that I earlier outlined, but there's one requirement that we so far haven't talked about, which is federation. So to incorporate federation support, we use the security assertion markup language standard, and we develop a SAML profile. Security assertion markup language is a very well-known federated identity management standard for exchange of security token, and it's backed by industry leaders such as IBM and HP, among others. So we develop a SAML profile where the idea is to have a SAML-compliant format for our attribute-based credentials. The SAML syntax is internally translated into an X-GTRBAC credential for internal use by the system. However, the benefit is that the use of SAML results in an interoperable specification. And it allows what's sometimes called single sign-on, that is seamless information access across heterogeneous administrative boundaries. And this is the architecture shown on the slide that we use. Note the decoupling between the authentication and the authorization module, so that the SAML token need not be provided by the authorization module, but can be accepted by the authorization module and generated by a separate authentication module. Here's the system architecture we use to implement our policy framework. I have a federation protocol on the next slide, but I'll probably discuss it over here. The numbered arrows represent the steps in the protocol. The user submits an access request, which could be a SAML request, and the access control module is able to process that request, convert it into an X-GTRBAC credential. It will then look into the policy database for the authorizations for the end user, which will also involve context evaluation. Subject to the evaluation of the constraints on user to role assignment and permission to role assignment, if the request is satisfied, then the access control module will contact the XML data source where the requested information is located. Once the information is located, it is then presented to the instance generator, because going back to the requirement of the propagation option in XML documents, the user may not have access to the entire documents but only to the sub parts of it. And the XML instance generator accordingly generates a a pruned view of the document for the requesting user, depending on their privileges. And subsequently, the document is returned for presentation to the requesting user. The session management module during this time keeps track of the state of the system, including the user to role assignments and permission to role assignments, and also enforcement of temporal constraints. So this is the Federation protocol, which in many ways is my favorite part of this work, because it brings together everything that we have discussed so far in very nice little steps, 6 or 7 little steps. And this can actually be translated. This represents kind of a pseudocode which can be translated into which can be programmed using a language to in the same series of steps to actually implement the access control policy. So we say that we have a federation protocol and an architecture, and we have tried to address a very important area in federated access management. However, this is not the end of all the problems, and nothing. It's not nearly as close to a perfect solution as we would like. We would have to integrate our solution with cryptographic mechanisms to ensure that nothing is lost on the wire. We would have to perform rigorous testing and validation of the policy framework to see if everything goes as planned, and so on, which is all part of our ongoing and future work. So lastly, we will talk about an application of this framework in a healthcare federation scenario. Because of our emphasis on software engineering methodology, we have used use case requirements for a well-known clinical document architecture standard for XML-based electronic health records. And this case study is aimed at secure access of electronic health records. As some of you would know, that electronic health records is a mainstream initiative of the federal government, and there is a regulation that all medical data in medical institutions across the United States must be transformed into an electronic form. In other words, electronic health records will become mandatory within the next decade or so. So clinical document architecture is a most widely used standard for XML-based representation of electronic health records. So the actors in this use case are creators and readers of EHRs, electronic health records that is, the patients associated with the records, the payers, and the institutions, especially the enforcers of legislation such as HIPAA, which is a very strong regulatory requirement to provide security and privacy for electronic health records. So we have a variety of use cases. We have about 5 or 6 different use cases which will be reported in my thesis eventually, but for the lack of time, I will discuss only 2 use cases here. Use case number 1 is that access policy for an EHR must have granularity at the level of the medical and administrative portions of the document. So going back to the propagation option, that XML document is hierarchical, it has multiple components, and not everyone can have equal privileges to access all components. Secondly, the granularity should be at the level of the category of the record, and thirdly, on the type of requester within the diverse actor population. Use case number 2 is that the portion of EHR retrieved by a permitted requester depends upon the requester and the disclosure rules defined on the EHR. So let's take a look at an example policy. For the first use case, we might have a policy that a US board-certified physician can access medical data in any clinical document, whereas a locally certified physician can access only documents of type discharge summary. These are our types according to the CDA type system. Another rule could be that a billing clerk can access only the administrative data in any clinical document. And so only a physician is allowed access to medical data, whereas a billing clerk should only be able to access administrative data. For use case number 2, we might have a disclosure policy that a billing clerk accessing an EHR of category clinical document can only access the document in first week of any quarter in year 2005 for a duration of 1 week. This goes back to our requirement that people who are dealing with finance work according to certain specified billing cycles, and their access should be restricted only within that period. For another rule is in this policy is that a discharge summary, the resource access is restricted to occur only from within the state of New York, and this could be a state law. Now this seems like a very complicated policy to enforce given that multiple systems are coming together in the federated environment and the requirements are pretty fine-grained. However, let's take a look at our policy framework and our policy engineering methodology and see how we can address this issue. The key idea here is that we have to define the credentials, the assignment rules, and the constraints that we need to enforce on the assignment rules. And our policy engineering methodology will allow us to construct the policy based on these modular language components. So let's go one by one. User credential. The ID of the user, we will again use the any keyword because any requester can try to access the EHR, and it's not dependent on the identity of the physician who's going to access the records. So we will use the any keyword for the user ID. We will include a board certified ID attribute because the access rules will be based on the board certified ID attribute of the requesting user. And so you will just drag and drop the UML classes within your application and include the appropriate components that you need in your access control policy. For the role, we need two roles, physician and a billing clerk, and we need an attribute for the role called location. For the permission, we need two objects, clinical document and discharge summary. And the document will have two portions, medical and administrative. And we will include one operation called HTTP GET. Our current prototype supports HTTP GET operation. In future, we plan to add more operations. HTTP GET allows you to access a resource online in a read-only mode. And that's probably how you access your websites every day. It's usually an HTTP GET operation. Next, we need to define a temporal constraint. And for this case, we will include a periodicity object and define a constraint valid for first week of any quarter. We will then need to include an interval object for year 2005 and a duration object for 1 week. All these come together to form a single temporal constraint. Finally, we will define the assignment rules. And for the user role assignment rule, the board certified ID would be either US or non-US, depending on the role. For the permission to role assignment, we will include the temporal constraint, and we will set the location attribute to New York. Sounds like a fairly straightforward way to implement a very complicated policy, but this is just the specification part. How do we move on from here? So remember, our UML profile for XML schema design allows us to translate this UML into an XML schema, which will then be used deployed in the system architecture we discussed earlier. And the XML schema documents will then be parsed by a custom parser that we have designed, and it will be able to store the policy information into Java objects within the system. And the Java objects will then be used by the session management module to enforce the access control policy once the users request access to resources. And so this is how we move from the specification stage to the meta-modeling stage, and finally we translate the UML meta-model into XML schema definitions, and we move from specification to meta-model and then to XML schema system, which is then translated into a Java bytecode, which enforces the access control policy. So you can view this policy to be represented at several levels of abstraction. The most formal being the BNF grammar, then it's abstracted out as a UML meta model, which then gets converted into XML schema definition, and finally Java classes and objects. I have links to the complete Java documentation of the Java classes in the paper, and hopefully it will be available in my thesis also. The prototype we have implemented is available in 3 versions. You have Windows-based shell, Unix-based shell. We have a Java web start to access the system from a client desktop, and we can also access it online from a web browser. I'll see if I have time later for a demo, or we can do it after the talk as well. If some of you are interested, you can come to me and I can show you a demo. So I'll just conclude with that because we need to leave few minutes for potential questions. So in summary, we have identified the key requirements for federated information sharing, and we have identified and developed, using a component-based approach, we have developed the key components of an access control policy language. And we use a policy engineering framework and apply software engineering principles to construct access management policies using the modular component-based approach. Our framework comprises of a policy language and a UML-based meta-model. Among other things, we have a federation architecture to realize the framework. It consists of a SAML profile and a federation protocol to allow federated information sharing in a federated database system. And we have an application that we discussed, and we gave an example of a healthcare federation environment. As it turned out that our policy framework, although it's applied to a federated database schema architecture in my thesis or in my PhD dissertation, the framework, because of being based on well-known software engineering principles, presents a formal methodology which is more generally applicable, and we are currently looking at other areas such as policy-based community establishment in ad hoc networks and other complementary areas where similar approaches can be applied and can be useful. I guess that concludes what I had to say, and if you guys have any questions, we probably have 4 minutes and 30 seconds. They promised they're going to kick us out of here as soon as the clock says 5:20. Yeah, go ahead.
Okay.
I can hear you.
Okay,
yeah, it's for the TV, I guess.
Yeah, in the permission to role and user to role assignments, you had these logical operators.
Right.
You could use an and or an or.
Right.
Can you arbitrarily nest those?
Yes, that's a very good question. We can. I'll try to see if I can go back to that slide, and I try to put those curly brackets there to give you the idea that if you notice if you notice in the overall grammar, an assigned constraint can have multiple assigned conditions. Assigned condition is a set of logical expressions on a given credential type. A logical expression can have arbitrary number of predicates, and an assigned condition can also have arbitrary number of logical expressions inside it. So that's a very good question, and that's partly what adds to the maintainability and modularity and flexibility of our approach. That you can. This also has implications in the federated system because you can combine policies from multiple sources, and you can include that in your constraint evaluation. So yes. Anyone else who would have paid enough attention to ask more questions? All right, I wish this was my defense talk because I'll pass with flying colors then. Okay, thank you very much.